In the last lesson, we considered the possible acidity or basicity properties of different salts when they were dissolved in water. We're going to flip the script a little bit here in this last lesson for Module 6 and consider how acidity in a solution might affect the solubility of an ionic compound, say a salt. Our learning goals are going to include how does acidity affect the solubility of a salt, and we're also going to spend some time talking about the chemical role of carbonic acid in nature, something that actually is very relevant to the local area here. Let's start by reviewing the solubility product, and just so we make sure that we're all on the same page when it comes to these equilibria. If we have a general ionic compound, written here as Mx, M sub M, X sub N, dissolving in water, it's going to produce M ions of Mn plus and N ions of Xm minus. All right, I'm trying to be totally general here. If you like to just use Mx, then it'd just be M plus plus X minus, but both of them form electrolytes in solution when they dissolve. And in many cases, we have very sparingly soluble compounds that don't dissolve much at all. So how would we determine the solubility of a compound like this? Well, we would first write the balanced chemical equation for the solvation, so that's what's written above. Then we would write an expression for the solubility product constant, which would basically be the concentration of the metal ion times its stoichiometric coefficient, raised to the stoichiometric coefficient power, times the concentration of the anion, X, raised to its stoichiometric coefficient power. We would then let little x, for example, be the amount of solid that dissolves. So that would then produce some amount of metal ions and some amount of anions. And then we would use the KSP value in the expression for KSP to solve for x and determine how many moles per liter are produced. So let's do an example just to show how this works. Lead hydroxide is a sparingly soluble compound, and let's say that it has reached solubility equilibrium, and what we might be interested in this case is it a toxic amount that's in solution. So the solubility of lead hydroxide would be PbOH2 dissolving into water to form lead plus 2 ions and 2 hydroxide ions. So if the amount of lead hydroxide that dissolves is X, then for each molecule of lead hydroxide that dissolves is producing 1 ion of Pb plus 2 and 2 ions of OH minus. So the amounts of Pb2 plus and OH minus would be X and 2X, again based on the stoichiometric coefficients. So when I form the expression for the KSP for this compound, it would be X times the quantity 2X quantity squared, or 4X cubed would be that expression, and it would be equal to the KSP, which is 1.43 times 10 to the minus 20. So that's the equation that you would need to solve in order to find the solubility of lead hydroxide. In this case, when we solve that equation, we divide both sides by 4 and then take the cube root, we would find that X is equal to 1.53 times 10 to the minus 7 molar. And so that is the concentration of the lead 2 plus ion. Now we can go further and express this, instead of in molarity, express it in grams per liter, and we'll see in a moment why that perhaps might be preferred, simply by multiplying by how many grams per mole are in lead. Lead is about 207 grams for every mole of lead. So if we multiply 1.53 times 10 to the minus 7 by 207, we'll get 3.17 times 10 to the minus 5, and that's how many grams per liter there are of this ion. Now one could look up on a table what the LD50 for lead is, and in this case it's 450 milligrams per kilogram of body weight. So let's say, for example, I'm interested in finding out if this is a toxic dose for me. I weigh about 70 kilograms. So I would take my body weight, 70 kilograms, multiplied by the LD50, 450 milligrams per kilogram, and then take that amount. That's going to be how many milligrams of lead would be fatal for me. And then from that, I would divide that by the number of grams per liter. So what's going to happen there is the masses are going to cancel out, and I'm going to get a quantity of liters that really constitutes how many liters of this solution I could drink before it would represent a fatal dose. And in that case, it comes out to be about 1,000,000 liters. So it's pretty safe that I'm not going to drink 1,000,000 liters of some lead-containing solution, so probably this won't be toxic. All right, but this gives you a way of, at least a model you can follow for how to solve for these solubility problems. Now let's look at a basic salt. So now this, remember, is a salt where the anion of the salt, in this case A, is the conjugate base of a weak acid. So when the salt dissolves in water, the Ma2, it's going to form an M plus ion and two A minus ions. Actually be an M2 plus ion. Sorry about the typo. In this case, the equilibrium is going to be the solubility product for Ma2, and it's going to be, we presume, much less than 1. Now, the same thing that happens, though, is when that begins to dissolve in water, the A minus it's a basic salt, so the A minus is going to react with the water molecules to form undissociated HA and hydroxide ions. So it's going to create a presence of some hydroxide ions, so it's going to have some base character to it. And the equilibrium for this reaction is just going to be the Kb for A minus, which is presumably less than 1. Now, let's suppose I add a strong acid. All right, and we'll see in a moment why that might be advantageous. That will cause a couple of neutralization reactions to follow. The first one will be obviously the OH minus that's produced when the A minus reacts with water. In the second of the red reactions, the OH minus will react with the strong acid that's in solution to form water, so it just neutralizes. The equilibrium for that reaction, this is just the inverse, the reverse of the water autoionization reaction, so its equilibrium constant is 10 to the 14th, so it's pretty large. This is effectively going to happen in completion. The other reaction that could happen is that the A minus, the basic anion that comes from our salt, would react with the acid in the solution to form undissociated weak acid, HA, and water. Now, the equilibrium constant for this is going to be 1 over the Ka for HA, because if you look at that second reaction, that bottom reaction there, if you thought about it in reverse, it would be the Ka reaction, so since we've reversed it, the K has to be 1 over the acid dissociation constant. And since it's a weak acid, the acid dissociation constant is going to be less than 1, so this K will be something greater than 1. So this is going to happen pretty quantitatively. Now let's review the steps that are happening here. A small amount of Ma2 dissolves. That's what's happening in that first reaction. Okay, and it's a small amount because KSP is not very large. Okay, we're then going to add acid, and that acid is going to react with the anion from the dissolved salt to make undissociated weak acid, HA. This effectively removes the anion from solution. So think about Le Chatelier's principle. We have something that's dissolving here. We're going to remove part of the electrolytes that are formed from that. Then what happens? More Ma2 dissolves. So the effect of this for a basic salt is by adding a strong acid, we can actually increase the solubility of that basic salt. So what is the net equilibrium of this solubility process? Okay, so if we combine these equations together, we would say the net equilibrium is going to be from the solubility process for Ma2, and then the acid-base neutralization reaction from the conjugate base of the weak acid, A minus, with the hydronium ion that we've added with the strong acid present to form undissociated weak acid and water. And since we've had to double this reaction to balance the coefficients with the first reaction, this is going to be 1 over Ka squared, which is a number that will be obviously much greater than 1. It's the reverse of the Ka reaction. So when we add these two equations together, what we'll have is basically the original salt, Ma2, as a solid, now be encountering not just a pure aqueous solution, but encountering an acidic solution because we've put strong acid in there. It will now dissolve to form M2 plus and 2 of the undissociated weak acids and 2 waters. The equilibrium constant for this net process is going to be the product of the equilibrium constants of the two reactions we just added together, which is equivalent to KSP divided by Ka squared of HA. And this, by and large, is going to be a number, because Ka is less than 1, is going to be a number that's greater than KSP. So in other words, we have increased the KSP, the effective KSP for this reaction, so we've increased the solubility. So what is our interpretation for all of this? We have added a basic salt as a solid to an acidic solution. The result is that it produces metal ions and undissociated weak acid. The equilibrium constant for this reaction is greater than the KSP, though I should hasten to add that it's not necessarily greater than 1, and we'll see an example in just a moment where it is not greater than 1, but it is greater than the KSP. So the net impact of all of this is that we can dissolve more of our compound Ma2 in this solution because it has acid in it than we could dissolve Ma2 in just pure water. So let's do an example using calcium fluoride. All right, here are our equilibrium constants. The KSP for calcium fluoride is 3.45 times 10 to the minus 11, and the Ka for the weak acid using the same anion, fluoride ions, the Ka for HF is 6.8 times 10 to the minus 4. So if we go back to our net solubility reaction, this would mean we're taking calcium fluoride, CaF2, it's reacting with 2 hydronium ions in this acidic solution to produce calcium ions, 2 of the undissociated hydrogen fluoride molecules, and 2 waters. The equilibrium constant for this, as it was before, is the KSP divided by the square of the Ka for HF. So it would be 7.5 times 10 to the minus 5. All right, this is not greater than 1. It's still a weak situation. Most of the calcium fluoride would remain as a solid, but a lot more of it is going to dissolve now because we have put it in contact with an acidic solution rather than a pure water solution. So what are some possible scenarios for this? What are the outcomes for doing this kind of process? Well, in pure water, we would just use the KSP for calcium fluoride, and when we solve for the amount of calcium ions that we would have in the equilibrium solution, it'd be 2.1 times 10 to the minus 4 molar. So that's the effective solubility of calcium fluoride in water. All right. If we were to create an acidic solution with a pH of 3, so the hydronium ion concentration is 0.001, well, now we see that the calcium ion concentration actually increases from 2.1 times 10 to the minus 4 to 9.5 times 10 to the minus 4. All right, so we have increased the amount of calcium ions appearing in solution, which means we've dissolved more of the calcium fluoride. If we increase the acidity still further to a pH of 1, we can see that now the calcium ions that appear in solution is 1.2 times 10 to the minus 2. So we've more than doubled. We've actually about 10 times the amount of calcium ions now in the solution because we've increased the acidity to a much more strong acid solution. If we go even further to a pH of 0, then we would have a calcium ion concentration of 2.6, so we've more than doubled it from the previous one. So you can see the trend here. As we increase the acidity, we're able to dissolve more and more of the calcium fluoride in the solution and increase the calcium ions that appear in that solution. All right, so this, I think, gives you a pretty good feel for what the effect of taking a basic salt and dissolving it in an acidic solution would do. I want to shift gears a little bit here because this is relevant to the issue of solubility in acidic and basic solutions, to talk about carbonic acid in the environment. Now, we'll start by saying, where does carbonic acid come from in the environment? It basically comes from carbon dioxide dissolving in water. So if you look at the first equation there, carbon dioxide dissolves in water, forms an aqueous solution of carbon dioxide, and then it will react with water in that solution to form carbonic acid. The equilibrium constant for that reaction is 1.3 times 10 to the minus 3. So, it's a reaction. It's not a strong reaction to the right, but it does occur, and that actually is the most dominant equilibrium of the ones that we're going to cover. The carbonic acid, in turn, can undergo a standard first acid dissociation reaction. So the carbonic acid reacts with water, forms bicarbonate ion, HCO3 minus, and the hydronium ion. And the Ka1 for that is 3.4 times 10 to the minus 4. Now, I want to point out that those two equilibrium constants are close enough together that we will probably have to include both of them in determining some of these concentrations. Finally, there's a second acid dissociation because carbonic acid is a biprotic acid. So HCO3 minus will again react with water to form carbonate ions in aqueous solution and more hydronium ions. But this has a much smaller, the Ka2 is much smaller than Ka1. It's 4.8 times 10 to the minus 11. So the net effect of this reaction is that we're taking carbon dioxide that has dissolved in water, it reacts with the water and ultimately produces bicarbonate ion and hydronium ion. Now you'll notice that I haven't gone all the way to carbonate ion, and it's for this simple reason. The chemistry that's going on here is dominated by the first two reactions. They have much greater equilibrium constants. They're not enough different that one of them dominates over the other, so they both have to be taken into consideration. But what they do is they establish equilibrium concentrations for the bicarbonate ion and for carbonic acid ion in solution. And they will also obviously create hydronium ion in solution, so it makes the solution slightly acidic. In fact, the acidity of the solution is it's got a pH of about 6.5, and this is precisely the acidity that you find in many natural bodies of water, in rainwater and so forth. So carbonic acid forms in the clouds, it falls down as rain, so the rain that falls on your head already is slightly acidic. It's not as bad as acid rain, but it is slightly acidic due to the carbonic acid that's in the air. The third equilibrium is the equilibrium that controls the presence of the actual carbonate ion in solution. All right, so let's try to unpack this a little bit. The first two equations are basically setting the stage for the acidity of the solution and the amounts of bicarbonate ion, carbon dioxide, and hydronium ion, all of those things that are present there. The key element that comes out of the third chemical reaction is the carbonate ion in solution. And the amount of that stuff that is in there has a very important factor in some of the environmental things that we are both enjoy and are worried about. For example, it is very important in the ocean because it affects how much sea creatures that form shells can actually form their shells if the balance is all wrong with the first two reactions. So I want to, though, focus in this lesson on a different effect that carbonic acid has in the water supply. And that has to do with the origin of limestone caverns. So what we will do is think about when this carbonic acid water seeps into the ground, so it's water that has carbonic acid, has bicarbonate in it, so in effect it is carbonated water, it's very slightly carbonated, that seeps into the ground. What happens? Well, it may encounter limestone, which is calcium carbonate, and that calcium carbonate is not very soluble in water. You look at the first reaction there, calcium carbonate doesn't form much calcium ion and carbonate ion because it's got a KSP of 3.36 times 10 to the minus 9. But this is one of those basic salts that's going to benefit a lot by being exposed to the presence of hydronium ions in solution. So if we take carbonate ion and add it to hydronium ion, what we'll get is a bicarbonate ion in water. That has an equilibrium constant of 2.1 times 10 to the 10th. And now if we combine those two, what we get is the effect of what happens when calcium carbonate encounters an acidic solution. In effect, what happens is the calcium carbonate will react with the acid in the solution. This is the third red chemical equation on the board. It will form calcium ions, it will form bicarbonate ions, and it will form water. But look at the equilibrium constant for that, which is basically the product of the two earlier equilibrium constants. The equilibrium constant now is 70. So instead of having a compound that hardly dissolves at all in water, we're going to have a compound that actually is going to proceed pretty vigorously to the right side of this equation. So the calcium carbonate is going to dissolve in this combination of carbonic acid and water. So what does that mean? Well, we've greatly enhanced the solubility of calcium carbonate in acidic solution. So what happens? Well, that happens underground in forming limestone caverns. You have a lot of limestone that basically is calcified remains of old sea creatures that lived when, especially our part of the country, was all under a big inland sea. And now when this slightly carbonic acid contained water seeps down into the ground, it can dissolve that carbonate, and slowly over time it carves out a big hole, which we know of as a limestone cavern. So if you've been to Natural Bridge Caverns, this is precisely how those caverns were formed. Now, it also plays a role in the formation of the various rock shapes that you find in a cavern. So in order to understand this, we need to understand that carbonic acid, that equilibrium, is reversed when it comes into contact with air. And in particular, what happens is that the carbon dioxide degasses. This is the same as a carbonated beverage. So when you open your Coke or whatever carbonated beverage you drink, it fizzes a lot. In fact, that's part of the attraction, I suppose, is drinking a fizzy drink. But what's happening is carbon dioxide is being released from the carbonated beverage. And this is exactly what happens now in a limestone cavern. Once the cavern is formed and there's air down there, the carbonated water reaches that air pocket, and the carbon dioxide leaves the solution, and it will affect then the equilibrium of all of the other reactions that we are interested in here. So what we see is that its effect is the following. So the carbon dioxide ordinarily reacts with water to form the bicarbonate ion and the hydronium ion. When we remove carbon dioxide from the solution, what does Le Chatelier's principle tell us? Well, we've removed one of the reactants, so the effect is that it shifts the reaction back to the left so that it forms more carbon dioxide. Okay, well, what's the big deal? I mean, so it makes a little more carbon dioxide, but it really isn't changing anything with the rocks. Well, there's another reaction that happens, and that's this one. Okay, when calcium carbonate in the acidic solution dissolves to form calcium ions and bicarbonate ions with water, now we have changed the acidity because the first reaction has shifted back to the left. It has removed some hydronium ion from solution. So you can think of the bottom reaction now has removed hydronium ion, and once again, Le Chatelier's principle tells us that the action, the shift in the reaction that will happen is to replace that. So again, we see a shift to the left. But now what is the net effect of this reaction? Well, we have taken calcium ions that were in solution, and we've now replaced them into solid calcium carbonate, so that we've basically replaced rock. Well, this is exactly how these limestone cave formations are formed. When the carbonated water that's seeping through the ground comes into contact with air, it releases carbon dioxide. That creates a chain reaction that now ultimately leads to the reformation of calcium carbonate rock. So that's why we see these stalactites hanging from the ceiling and stalagmites coming up from the ground. Basically, we have reversed the reactions that have caused them to dissolve in the first place. Now, there's one last effect that I want to bring to your attention, and that's we saw in the first lab exercise that dissolving gold in water actually involved creating a complex ion of gold. And it took gold, which ordinarily does not dissolve in water at all, and made it susceptible to dissolving. So we could make gold more soluble in water by basically putting in an ion, cyanide ion, that made the gold form a complex ion, which then would be soluble in water. Well, gold's not the only one that can do this. We can also have a similar reaction with silver ions, and they form a complex with ammonia. So for example, if we have a compound like silver chloride, which is not very soluble in water, it's got a KSP of 1.8 times 10 to the minus 10, we can make that more soluble by simply adding ammonia to that reaction. So here we are, we've added a base, although it's more important that the base tends to form a complex ion with the silver. But in forming that, we have removed silver ions from the solution. And in removing silver ions from the first equilibrium, we have caused Le Chatelier's principle to again shift the reaction back to the right to replace those silver ions, so it makes more of the silver chloride dissolve. The net reaction for this process is going to be that we have solid silver chloride reacting with two ammonias to form the complex ion, the silver ammonium complex ion, and chloride ions. And that equilibrium constant, again, tends to be greater than the solubility product constant of the original silver chloride. So this aids the solubility of silver chloride in water. So I hope this has helped you learn something about how acidity can affect the solubility of a salt. I hope it also has informed you a little bit about how carbonic acid plays an interesting role in the formation of limestone caverns and rock formations within those caverns. Thank you.